Okay, well, we do have a full schedule with 5 speakers, so why don't we get going? My name is Bob Chen. I'm with an organization called Season, which is part of the Earth Institute at Columbia University in New York. And I'm here both as a person who operates on the supply side. I run a NASA data center called the Socioeconomic Data and Applications Center. And I'm, among other things, I'm also co-chairing a new thematic group on sustainable development data of the Sustainable Development Solutions Network. So looking at the issue of how new kinds of data and tools, as you're going to hear about, can be connected with the need for better data at all levels of sustainable development decision making. So it is my pleasure to introduce a great group of people who really have been working with all types of big data for quite a long time in some cases, or in other cases, pretty new and recent stuff, some of which you've seen bits of, and so we'll have a chance to hear a little more depth on what's going on in these different organizations. You see the names and the affiliations of all the speakers on the screen, so I'm not going to go into any detail, but we will be going in the order in the program, and I guess the order up there, starting with Stuart Menchin, who is from, it doesn't actually say, it says Chief Environmental Geoscience Division, but in Geoscience Australia. And he's also the representative of Australia to the Group on Earth Observations and the UN Global Geospatial Information Management Initiative. I'll just go through everybody and we'll get it out of the way. Ilia his name is now spelled correctly up there, Ilia, is Director of the Spatial Information Systems Lab at the San Diego Supercomputing Center and the University of San Diego, obviously, and I'm sorry, the University of California, San Diego, obviously in San Diego, California. Ilia is, I think, mostly talking about EarthCube, but he's plugged into many other networks in health, in Open Geospatial Consortium, and lots of other things that he's been working in for many years. Mark Reichert is the President and Chief Executive Officer of Open Geospatial Consortium, which I hope most of you already know about, but Mark has been president for 8-9 years. So, yeah, you've been at OGC for 15 years, long time, and was at the Federal Geographic Data Committee in the US before that. Brian Sullivan is Program Manager for Oceans and Google Ocean and Earth Outreach. Is that the right? Close enough. Okay. And I think he's been at Google since 2007. And finally, Stefano Nativi, who's the at research, what's CNR, French Research Council, thank you. And has been very heavily involved not only in Geo, but in Inspire implementation in Europe and many other activities. So they'll tell you more about that as they go along. So first speaker is Stuart Menchin.
Thank you, Bob. So we've heard a lot in the last day or so about the need to make Earth observation data more accessible and useful to decision makers. We heard this morning in the plenary, particularly from Chris Tucker, of the power and importance of spatio-temporal information and using the power of looking through time and space to understand change. And traditionally, remote sensing and the use of satellite imagery requires a lot of expertise, a lot of processing time and expense in moving from the raw satellite image through to a product that contains information that's useful for people. And it's our view that we really need to move to a new paradigm away from processing individual satellite scenes one at a time or groups at a time and processing it through to a product. Move into a paradigm where we're actually looking at collection level analysis, looking at the whole archive of our Earth observations. And that's what I'm going to talk to you about today, the Australian Geoscience Data Cube, which is really a data infrastructure that's intended to lower the barrier for entry to people that don't have remote sensing expertise directly, making the full archive of our Earth observation information available and improving the efficiency, cost and speed of development. This thing that I'm going to show you is open sourced and based on open data. So while we've done this for Australia, we think it has global applicability. So without further ado, I'll move into the presentation. So first up, what we've done to build the Geoscience Data Cube is moved all of our historical satellite imagery from our archives, our tape archives in the basement of our agency, across onto our national supercomputer facility. It's on spinning disk there, so we've actually then utilised this large collection of data going back 40 years over the Australian continent, and we've calibrated it all through to surface reflectance information. What this means is that you can compare a pixel from a Landsat scene in 1979 with a pixel from today and be confident that you're actually looking at the same measurements. You can compare a pixel on one side of the country with one on the other side of the country and those measurements are comparable. So by calibrating the whole archive up to this point and then lining up and georeferencing this through time, we can actually create an analytical engine that allows us to ask questions of it rather than taking the data to our own computer to ask questions directly. So to do this, we've actually had to line up all of those satellite scenes through time so that we're confident we're looking at the same point of the planet. Now that's relatively easy. As you can see, if you've got 4 scenes here, you can arrange them so that you're looking at the same 25 metre pixel through time, and that's easy to do. But when you're dealing with a situation where there are 640,000 scenes of Landsat data, for example, across Australia over 40 years, you've actually got a real challenge in aligning all of that. And in fact, the Australian continent has moved 2 metres during that time. So the latitude and longitude of a Landsat scene today, you're not looking at the same land as you were 40 years ago. So you've actually got to correct for continental drift in adjusting all of this data, which is a big challenge. So effectively what we've done is moved all of this, this data's been collected by overpasses of satellites, but we've actually arranged them into data cubes so that we're actually building up a dense time series of information over every part of Australia, and every pixel within each of those data sets actually lines up through time. This allows us to analyse the entire continent at very fine scale, and we can ask questions of this data set and throw scientific algorithms at the data and see what it tells us. So here's an example, zooming into one area where we're looking for the presence or absence of water. So this is just looking through this dense time stack through 40 years of data and saying, well, where was the water at particular points in time? So the animation you're seeing here includes, you can see clouds and a range of other things. We maintain every bit of that data, even if it's a cloud pixel. Knowing that there's a cloud pixel there is actually useful to an analysis if you're a weather person, for example. We don't treat it as rubbish. One person's rubbish is another person's gold. We maintain all of the data and we maintain the provenance of every pixel in the data. So the analysis you just saw there, here's the same analysis. This was actually the first one that we did using the data cube, and this is looking at 15 years of data from 1998 to 2012. We're talking about data coming from 1,200 individual Landsat scenes. So the traditional technique of downloading a Landsat scene and processing it, that would take roughly half an hour per scene. You'd be dealing with weeks for the downloads of those individual scenes, and you'd be dealing with months of effort to calibrate it all. Instead, this analysis took only 15 minutes to complete on the DataCube infrastructure. It's worth mentioning that over 15 years, this scene here is 4,000 by 4,000 Landsat pixels. That's 16 million individual pixels by 7 spectral bands by 15 years of data. We're talking about 40 billion observations just for this analysis. What you're going to see here is the footprint of water over that 15-year period. You can see up here we've got a lake where there's irrigation occurring, and you can pick out when those fields are flooded. As we march into the drought years, you can see these lakes starting to dry up, and as the drought progresses towards its completion, pretty much all the water dries up in those lakes. So you can produce these kind of analyses very simply from that data set. You can then actually collapse that into 2 dimensions and say, where was it always wet during that 15-year period? These are the permanent water bodies. And where in the red areas was it wet only once or twice? And these are the floodplains. So you've got a picture of the frequency of water inundation across the area. This worked very well. As I said, 15 minutes. We thought that was a good success. So we said, let's do this for the whole country, an entire continent. And it's a product we now call Water Observations from Space. What we've done is now gone back 27 years of data through the entire Landsat 5, Landsat 7 archive at 25 metre resolution, and the data that fed into this analysis came from 300,000 individual Landsat scenes. Now, if you were downloading those scenes and processing them in the way that we've always done, that would take you 17 years to download the data before you actually did the analysis. So instead of doing that, what we did is we threw the question, where is the water, to the 93 by 10 to the 12 individual pixels in the data cube, which is 3/4 of a petabyte of data, and it takes 3 hours to produce that product from go to woe. So we can actually ask these kind of questions, and in 3 hours you've run an entire continental analysis for 27 years of history, and you've got a rich time series that you can then explore for information. I'll also mention just here that 300,000 scenes, when we used to have to charge $1,000 per scene before the Landsat data was made freely available. So that's a $300 million product, right? Free now. So here's an example of the output. So what you can see here is the footprint of water. You can see some more permanent water bodies here. This is a cotton farm, some less permanent water bodies in the natural floodplain. You can actually analyse this. This is now set up as an OGC web service, this product, and you can interrogate this through time. So you can click on any individual pixel across the entire continent and see how often it's been observed, how often it's picked up water at that location, and the percentage of time that's happened. And then you can actually look through time and see when that's occurred. So you can actually see the timing. This particular 25 metre pixel at this point in the continent has been flooded on these dates where the blue dots appear, and it's been dry where all the red dots appear. So you've actually got an entire history through time over that period, 27 years, telling you which bits have been wet and which bits have been dry. Funnily enough, this we didn't realise when we were developing this product, but this is actually a coastal change detection tool as well, because the presence or absence of water happens every time the tide goes in and out. So just from this one analysis, which is looking for presence or absence of water, you actually get a coastal change detection capability. Let me take you through this. So there's an island here that has changed shape from 1988 to 2013. And what you can see down on the left is a sandbar. And if I click on that, you can see that that's alternated from being picked up as land to water as different tidal stages have occurred. But it hasn't changed state. If we look at the yellow pixels, they've gone from being land to water. This is coastal erosion, right? And the green pixels have gone from being water to land. That's coastal deposition. So here you have an objective measure at 25 metre resolution for an entire continent about how the coastline has changed for the past 27 years. Just from asking this one question, where is the water, and where could it be? So now I'd like to make the point that that's one algorithm, presence or absence of water, but we can run all algorithms on this. Just about any algorithm that you've created products for in remote sensing, you can ask of the data cube. So here's another example. In this case, we're asking for the proportion of green vegetation, dry vegetation, and bare soil. And we're looking at this grey dot up here, which is this field. And what we can see is if we look at that proportion, it changes over time. So what you're effectively looking at here is the cropping pattern of that field over that period of time. And we've got a period where it's laid fallow, a crop's been planted, it's matured, it's been harvested, it's laid fallow for 2 more years, crop's planted, harvested, and there's another crop in play at that point in time. You've got this record for every single 25 metre pixel across the entire continent. So you can generate these kind of products very simply, 3 hours, you press the button, you run a new algorithm across the entire continent. So that's the data cube. We've already prototyped algorithms for forest cover change, carbon accounting, water quality, seagrass mapping, bathymetry, bushfire scar mapping, mangrove change detection, and many more, all using just this infrastructure and asking the questions of throwing different algorithms at the data rather than taking the data away and doing separate analyses of that. I'd like to leave you with 2 points. This is not just about Landsat. Right? We've done it with Landsat to start with, but the structure that we've developed here is suitable for all Earth observations, and we're currently loading MODIS, the European Sentinel data, and it could quite easily take the Planet Labs data that was talked about, the CubeSat stuff, into the future. It's about actual measurements of this point in time and space. So this is the Geoscience Australia Data Cube. The data already exists to do this across the rest of the planet. All we have to do is get organised and structure the data in this way elsewhere, and we've actually got a global change detection tool that could produce this kind of accessibility everywhere on the planet if we wish to. Thank you. Great.
Thanks, Stuart.
Hello, my name is Ilia. I come from San Diego Supercomputer Center, but I will talk not about large volumes of data that we can process, but about different V in big data, about variety and how we try to integrate data from different types of geoscience resources into something that can be searchable and integratable. The program is called EarthCube. That's a large initiative that NSF started in 2011. So I'll have a few slides about that program in general, and then talk about our small piece of that large system that deals with cross-domain data discovery. So what is EarthCube? As I said, it's been started as a large-scale NSF initiative in 2011 with the goal to create cyber infrastructure that would unite entire geosciences, that will make it much easier to access available resources, data sets, software tools, models that have been developed in different branches of geosciences, and make it easier for people who are not currently actively using large computing resources to use that. And this is to give you the size of the problem. In geosciences, there are multiple domains. This is a list of a diagram that shows you programs within Geoscience Directorate at NSF, and each of them stands for perhaps some branch of geosciences in which there may have been developed one or more information systems that deal with different data types used in that subdomain. In some of them, nothing has been developed, so there's a lot of huge variety and differences between these systems in terms of what kind of resources they have and how they organize that. It is a fairly challenging task and somewhat similar to what has been discussed in the GNON sessions here, where you have multiple types of resources organized in or not organized yet in observation networks, and you want to discover them and integrate seamlessly. Here we're talking about all types of geoscience resources that you want to bring together. We can try to think of high-level information, high-level design for EarthCube, such as you have research sites where a lot of ground research is being done. People collect data, develop models. Then if there is some community organization, then these data and model results get into domain information systems, and these are organized currently as silos, as stovepipes that don't really talk to each other. The main goal of EarthCube is try to create that additional layer on top where resources that have been developed within each of these systems would be possible to integrate and reuse from other systems. If you think at this, if you look at this middle layer, if you want to reuse data from another domain, you would need to find it, understand what's in the data, retrieve the data, and then integrate it with other data, which means these four components would translate in each system having a catalog, some kind of semantic framework, vocabularies, data access services, and information models for integration. So that's a very crude, high-level model of how we can represent the domain. And then at the upper level, you would talk about vocabulary crosswalks, catalog federations, common set of services, and that's what have been discussed in the Genome session and other sessions as something that would depend on standards that have been used to expose all of these four components for each domain. This is a moving picture, of course. Different domains are in different stages, but the ultimate goal is to create that upper layer and to have hello? Maybe next slide, if you can click there, because it doesn't work here. Okay. All right. And the main thing is to bring geoscientists into the picture, so that's too far. All right. I'll skip that. But the main thing is that the information structure has been developed separately from community involvement. And the main thing is to have geoscientists participate in using this system, creating resources into the system, and providing feedback as to how the system works. This is how the initiative is organized. There are several types of projects being funded. Projects focused on community organizations, so-called RCNs, Research Coordination Networks, building blocks that actually build some components of the infrastructure, and conceptual design that try to propose how the system should work together, should work in the long run and self-evolve. So you see that currently we're sort of in transition between the initial prototyping and demo phase into kind of more refined designs and more advanced prototyping phase, after which there will be construction. I'll talk about one of the building block projects within the EarthCube initiative called Synergy, which stands for Community Inventory of EarthCube Resources for Geoscience Interoperability. So Synergy is an abbreviation. The idea is that you have these multiple information systems. You want to have a one-stop shopping. You want to search all of these resources from one place. Currently, it's not possible because there are multiple catalogs, but they all follow different schemas. They follow different semantics. And when we try to harvest information from these catalogs and do search over it, it ends up very messy. It doesn't really work. Also, there are lots of types of resources that do not show up in the catalogs. There's some hidden knowledge within a domain about what types of resources people use, but that never shows up in information systems. So we also work with community groups to domain inventories of resources. So how to get rid of that big mess that we end up with when we harvest information from different catalogs? We pass it through a pipeline that makes this metadata more complete and adds missing pieces, and makes it compliant with standards so that you can have a common search interface over different metadata sources. It works by, so the first step is harvesting metadata from different catalogs. Then we load this in a staging database and have a bunch of information enhancers or metadata enhancers. So for example, if you have missing spatial extent in the metadata or missing keywords, the system will go out and figure out how to fill these gaps and create much fatter ISO documents that will have all this information in it, including semantic references, because one of the biggest things in organizing large information systems is adding semantics to your resource descriptions. This is the way that is envisioned in GNON, as I understand, where you want to use this as bridges to create networks over resources. And but the biggest problem is how you annotate semantically existing resources. So what we're trying to do here is we're trying to do this automatically. And the types of keywords that get assigned reflect what we extract from abstracts that exist in the metadata, or from other text that we assemble by crawling around URLs that are pointed to in the metadata descriptions to reflect materials, processes, equipment, and a few other dimensions in the data cube that we're essentially building here. So you end up with a lot of keywords getting assigned to a document, and these are categorized by the types of types of keywords that I just mentioned, and then it is given to a curator who would say, you know, this is correctly assigned, this is incorrectly assigned. Then it goes to machine learning, and eventually the system learns better assignment of keywords of different semantic types and spatial extents. So the next part is working with the community, and we have a system where we developed a fairly easy way for community groups to come together and contribute resources. They would work with Google Spreadsheet, and on top of Google Spreadsheet there is a system that is hot linked to that will present these resources via very nice visual interface using the system called SWAF. SWAF stands for Survey Analysis via Visual Exploration. And we've been using that in a number of contexts for presenting inventories, but also for applications that range from biodiversity to people, galleries, to archaeology, to other fields. In these applications, you would see distributions of resources and can navigate to these resources as organized by different community groups. So that work has been done with several RCN projects, including projects that focus on environmental omics, on paleogeosciences, on coral reefs and sedimentologies, those that do not have well-established catalogs yet and are only in the process of constructing those. So just to summarize, we feel that creating inventories of information resources is a key thing. You need to know what exists before you want to build something on top of it. And we also envision EarthCube as a system where there are several main components. A registry of frameworks in which you use to describe resources, the large catalog of different types of resources, and sort of evaluation system that tells you how whether these resources are compliant with standards and how they have been used, as well as environment for composing new infrastructures from existing components. This is a fairly high-level model, but we were trying to follow that because going to level of individual systems would immediately break as we try to cover too many different types of data. The synergy metadata enhancement pipeline that we developed, we believe can be used to replace manual data curation with automatic data curation. When you try to publish data and have brokers operate on it, the quality of metadata is critical. If your metadata is missing essential pieces, then the quality of your brokering will be less good. So what we are trying to do is to bring everything up to the par, fill in the missing pieces, and typically it's a very manual, time-consuming process. We're trying to do this automatically and include this as part of data curation systems in different community groups, in different repositories. Yeah, so that's all I wanted to say. Thank you.
Thanks, and thanks for being pretty disciplined. So, Mark, your next one.
Thank you. I'll try to move quickly to keep on time. Good afternoon, everyone. I hope lunch was good, and I hope it's not settling in and forcing you to go to sleep, because I'm going to talk a little bit about standards, but they're really essential. Yeah, we need the next presentation up. I can do a song and dance if you'd like, but you won't enjoy that. Anyway, I represent the Open Geospatial Consortium, a group of about 515 organizations around the world that are building open standards to support the access, integration, fusion, and use of geospatial information in decision making. What I wanted to do is to talk a little bit about what we're doing within the standards community in OGC to deal with what we call big geospatial data activities. And I just pulled a recent article off the internet. The topic big geospatial data is actually becoming a term of use. In this particular article, the author noted insurance pricing, emergency response, drone activities, food production as all areas where big geospatial data is creating a difference. And as we all know, it goes on and on. But I thought it was really good that this is being recognized as a term and of importance to the community. Geospatial data obviously is big data by its nature, and it's expanded by the fact that each of us are sensors ourselves as we carry cell phones and other equipment around, and that we're part of a social sensing environment. GIS also moves us into the cloud, and we need to be careful, and I think our previous presenter said the days of downloading data to compute are pretty much fast approaching Neverland. We don't want to do that. We want to move our processing closer to the data so we can gain great economies. And then accessing in the cloud using the OGC standards framework is something that we've proven to be very efficient. And then we're moving more and more into this area of what we call high velocity and streaming data as part of a big data environment. As an example, here's the Integrated Ocean Observing System in the US, part of the Global Ocean Observing System, with thousands of assets linked together using open standards, millions of observations. So if we're going to do our work to try to make meaning out of those observations for different analytic processes and results, we really need to look at this as a big data problem. I want to talk a little bit about some of the OGC big data activities that are going on right now. And first I'll show you the OGC standards framework. I'll spend about 10 seconds on this. Geospatial standards to allow you to discover and integrate geospatial information from different sources, share it with different clients, the ability to integrate sensor data, whether they're fixed or mobile sensors, a number of standards for processing, and then a whole bunch of encodings that allow us to address the needs of data transfer between different communities. With that said, there's some interesting standards that are really making a difference in the community right now. One is the web processing service. This is really an envelope. It's a standard that allows you to plug in an algorithm, whether it's a very thick algorithm or a thin algorithm, anywhere in your service flow so that you can process sensor data, make more meaning out of it, deal with functions of data cubes, as was discussed earlier, and create interoperability so you can move algorithms around and test them and trial them. And one example of an implementation of that in a big data context is Imagery, which is part of a D4Science program in the European Union. This is really a sort of a hybrid information infrastructure for researchers. But in this particular case, and there's several others, we're using web processing service to do analytics in a Hadoop framework. So this is really big data processing enabled by open standards, the OGC web processing service being only one of those. And then after the Fukushima incident of a few years ago, that terrible tragedy, our Japanese members, along with other Asian members, introduced the concept of moving features. So we're all familiar with situational awareness and static maps and static displays. Moving features themselves, vehicles, people, other objects, this is a high velocity issue, and it's one for big data. So this standard, which was just approved a few months ago, is now part of our architecture and is being adopted to allow the analytic activities and visualization of moving objects and features. And what you see here, if you could see the animation, is the before and after the tsunami and the power going out in Tokyo, and the rates at which objects are moving. And that's really telling in an emergency situation. We're also working in the area of smart cities. You know, we have the geospatial information, we're fusing the built information, we're fusing sensors, and we're also doing modeling of processes in a city. And so this is an activity that OGC is working on from a standards perspective with many partners in the standards community. And I don't have time to go into the details, but you can go to our website and look for a Smart Cities Spatial Information Framework document that explains the detail of what we're doing in that area. And then I want to talk a little bit about discrete global grid systems, and I hope we come back to this as a panel if we have time. With big data, I think it's going to be difficult to use traditional coordinate reference systems. It's just there's too much data, it's flowing too fast. So there are a number of discrete global grids out there. These are grids that have nested tessellated cells. I love the word tessellated, I had to use it today. Or point reference grids. And there's different types of grids that are being used to really allow us to organize information on an Earth system. And what we're doing in OGC is not developing a particular single solution, but we're really looking at all the different options and recommending best practices on how those different grids can be deployed and used in a big data environment. And then furthermore, I believe the working group's trying to find ways in which to work between those grids, how we move between those grids when we have to do information sharing. That is also documented on our website as part of a standards working group. And the idea there is to create common criteria to define conformant grids and then develop conceptual standards, the best practices to facilitate fusion and organization. There's some other standards that we use, Web Map Service for visualizing raster information. One of the more interesting ones is called the Web Coverage Service, where you can now start working with multidimensional, multispectral data in a big way. Every pixel, every dimension has attributes. And I believe in the case of Australia, we were using the Web Coverage Service with an encoding called CFNet CDF, which deals with climate data, to actually move that information around in and out of the cube based on well-known scientific encodings that are accepted by the community. What's interesting about this environment is that this is a European Commission, European Union project called EarthServer, which is using Web Coverage Service along with other OGC standards to move in and out of these data cubes, essentially, these environments. I know at its inception it had 6 100 terabyte databases. We checked a couple months ago, it's now at 20 132 terabyte data sources, for marine and planetary science and different applications. So this stuff is getting real, and standards are a bit of an underpinning, and they're helping to make a bit of a difference in terms of being able to gain access to, use of, and efficiencies in these environments. This is an example of a recent testbed we just finished. This is really the invocation of a whole bunch of processes, including a web processing service to allow first responders to apply different types of analytics to the problem. And let me go back. So in this particular case on the left, there is a diagram of different components that were used in the testbed. What I'm trying to show here is that in the case of emergency response, you can dynamically apply fairly big data analytics to deal with problems that are happening on the ground at the moment. In this particular case, what you're looking at is the runway of the San Francisco airport and a computation of what a climate-induced storm would do in 2025 based on a 1.5 meter increase in sea level and then a flood surge. So what attributes of San Francisco would be underwater? How would we deal with that in an emergency? So it's really interesting to see how big data can be applied to immediate real-time problems. And then we've also been looking at the efficiency of processing in the cloud, going back to the comment, take the processing to the data, stop downloading. I think you said, 17 years or something like that to download, to do the work that you did? So what we're trying to do here is to demonstrate the efficiency of putting open standards, including those of the OGC, up in a cloud environment, and as well as negotiating between different cloud environments. And so we've done some testbed work on that with some really good results. We've also looked at some of the processing efficiencies of putting our standards up in the cloud, and it's fairly flat. I mean, it's very, very efficient and very flat when you move to the cloud in terms of efficiencies of these OGC services that can be stood up. So what's in common to all this discussion is obviously location, and that's our specialty. We don't claim to own this space, but we do wish as an organization to advance our geospatial standards to be consistent with the needs of the big data movement, and at the same time working with the broader standards community and the user community to make sure that all these standards work together to make it much easier for us to move ahead in this environment. So the standards community, including OGC, is working together and quite collaboratively. I don't know if you, in other sessions we work with W3C and other organizations to deal with these types of issues, plus the ultimate issue of semantic mediation between different communities and data sources. And we're extending our architecture with those communities to deal with analytics, multidimensional, multi-temporal visualization, processing, and other activities in the cloud, including the integration of volunteer geographic information and crowdsourced information. And I might add that we're also addressing spatial IoT. So how do we bring IoT devices, those flows into a spatial and temporal context for analysis and use? So from smart cities to climate to other activities, our work has just started, but I ask you all, if you're interested, to please join the community in helping us move forward to create greater efficiencies. And with that, thank you very much.
Thanks, Mark. Ahead of schedule.
You want to take longer?
We might have time for questions and things. So.
Fair point. It's very kind of you. We'll give back to the community. Hi. So my name is Brian Sullivan. I'm part of Google has a special team we call Earth Outreach. And the goal of Earth Outreach is how do we leverage all of Google's geospatial computing and other engineers there to make a difference in the world for public benefit. And we have a couple different areas that we focus. A lot of it's around the environment and conservation. We do a lot of work in public health. We've done work with indigenous cultures. Within those areas of the environment, we've started to build certain vertical leads around forestry, water, fisheries, and now we're doing air quality and climate. So some of the partners we've worked with in the past, and if any of you want to attend the next session that I'm speaking at, we'll speak more about some of the work we've done with indigenous communities and also with fisheries. Now, many people are familiar with Google Earth, and it's a wonderful tool to kind of visualize your world. And so here we are in the middle of the Amazon in Rondônia, Brazil, and you can see how deforestation is changing this over time. And this was a tool that anyone could go in and see that, and they would see segments maybe every 4 or 5 years when a new satellite image was taken. But they couldn't compute anything. They could only look at it. So we said, we think there's another platform that needs to be built for massive geospatial computation that will work with Google's big data. And from that, we've built something called Google Earth Engine, which is the majority of my talk today. So as many people have commented before, there's a series of satellites out there. I'll skip over a lot of this because I think most of you are familiar with it. Landsat 8, for example, there's probably over 3.6 million images over the last 40 years. There's many other satellites out there. Again, I think many have spoken to this, so I'll skip it. And the good news is this was historically very secure. So these are all more than a petabyte of data stored at USGS. And as people mentioned, this was very difficult to get to. You had to order it. They would ship it to you on a drive. And so the first thing we said is let's put it all in one place where everyone with an internet access can access it. So there are a few trends that we saw happening in the technology space. One, bandwidth was dropping at about 25% per year. Disks were coming down about 40% per year, and CPUs were coming down the fastest. And so what we came out with that is that bandwidth is the most expensive, so we need to put both the data and the analysis next to each other. We want to do everything online because disks are cheap. And finally, because it's so easy to recompute things, we don't store much. And so those principles brought those tapes to a modern day Google data center. And then we went back, and in addition to Landsat, we've been gathering many other sensor data as well. And today we have the largest public data catalog with over 5 petabytes of data at your fingertips that anyone can access already. We've also been adding Sentinel-1, we have MODIS, we're starting a global DEM or elevation project, and we're adding to this every day. So how does it work? The idea is you take some image from a satellite system, you break that up into smaller components, we parallelize that off to thousands and thousands of computers at once in our data center. Each of those computers then runs a calculation on it. In this case, we're trying to classify what's land and what's forest and what's non-forest. We then put that back together and we have a single image. And because we can parallelize everything, we can do this very quickly. So here's a very common story that you hear. This is one image that's coming from Landsat. And you can see there's a lot of striping in this, and there's clouds. So instead of looking at one image, we take a stack of them throughout the year, we run some basic math on it, and then we have a composite image, which looks a lot more like what you'd like. So we say we can do this for a region, and similar to what Stuart's done, I'll go back to that. There's lots of places we can apply that. So first, let's go through some visualizations. This is Borneo. You never get a cloud-free image here. But by taking a year's worth of data from that, we are able to produce this, the first view of Borneo. We did this for the entire continent of Latin America, and then we did it for the entire world. I think you quoted your cost was roughly 300 million or so for the world. We thought this was about $1.2 billion. Since then, a lot of this data has been made publicly available, so these are fun dollar figures we get to throw out, but they don't mean what they used to a few years ago. So this was very helpful to produce basically one frame of what the Earth looks like without clouds for 1 year. So we said, let's go back and do that for everywhere in the world for the last 40 years. What can we find if we can watch the Earth change over time? This is Las Vegas sprawling. Next to it is Lake Mead. There may be a correlation that as Las Vegas grows, the demands on water are also increasing. This is in the Amazon, deforestation. You can see the original logging roads, you can see spiders spreading out from that and how that changes. This is in Saudi Arabia, drip pivot irrigation, food in the middle of the desert. This is in the middle of the Amazon. You can see how the Nile changes over time. If you're that village right there, you've either just lost your water source or you've been hit by a new river you weren't expecting. And of course, this is Dubai, just down the street, being built out over a period of a few years. This was a large project we did with Time Magazine. The idea being you could go anywhere in the world and see how this is changing. I think we've all been speaking about the sheer size of what's happening on this. To do this on a traditional high-end workstation would be longer than any of our lifetimes. We're able to turn this out in about a day and a half. And I think the big message is that these are tools that are available to anybody that wants to use them now. Looking at forestry, we've moved from doing just visualizations to hardcore science behind this. Working with the University of Maryland and Matt Hansen's lab, we've come up with the first global map of how forests have been changing over the last 12 years at an individual 30-meter resolution. These data products are then often rolled into bigger, here's one example. Looking in Sumatra, we're going to see red is going to be forest lost over the last 12 years. On top of this, we traditionally lay other critical endangered species habitats. Do you know what keeps cutting out? We also do marine or protected areas and see how that's changing as well. A lot of these data products are then loaded into other nonprofits that are building broader programs. So instead of just looking at the scientific data behind it, they're bringing in policy information. They're making tools available for media. They're making tools available for journalists. And this is changing a lot of things about how people look at logging and adding additional political pressures. I think Global Forest Watch has been well discussed, so I'll move on. And then also we're creating very intuitive environments for people so they can select an area and get calculations like this without having to dig into any of the code or the science behind it. And what's wonderful about this is the technology is produced in one region, can be used anywhere else in the world. So a lot of these tools are now being used in Indonesia, for example, around law enforcement. Looking at water, Stuart, I was thrilled to watch you basically give my presentation a little bit earlier. So we've been doing this with JRC, the Joint Research Commission out of the European Union. The idea being when looking at a lot of these images, it's not always clear where the water is and where the water isn't. Computers are really good at figuring this out, and so we can do that. But of course, the interesting piece is when we look over time. So here's another example in Australia. And what we've done from the color coding here is very similar to what you did. The darker blue is something that's been water the entire time. And the lighter pink would be something that would be water a smaller percentage of the time. And so you can see how these lakes are drying up over time and where there's still water. One more example of this is the Poyang Lake in China. This is the largest freshwater lake in China. It's very seasonal, depending on flooding and also when dams have been put in. At its peak, it used to hold approximately 3,500 cubic kilometers. We've seen that number go down in the next time period, and now it's down to about 200 square kilometers. This is the home of millions of migratory birds that come through here, so there's obvious environmental impacts to this as well. I'll skip over this one for now. Similar to what you were showing, it could be used for a lot of different types of evapotranspiration. We can understand what types of crops are using water, which ones are in different stages, but I think you've covered that. So something new that Google's starting to play with is air quality. And we have street view cars that we're driving all around the world. And so as long as we're out there capturing imagery, why don't we collect all kinds of data as well and make that available? So obviously air pollution is said to be 9 times deadlier than car crashes. The WHO is saying that it's a leading cause of cancer. So how can we start measuring this and making that data publicly accessible? So we have a standard Google Street View car, and on that, in addition to the camera on the top, we've added a lot of other inputs for air quality. And then the data coming out of this will be made available to any scientist that would like to use it in Earth Engine. So you can see some of the things we're collecting on climate change around methane and carbon dioxide. And around human health, we're doing things for particulate matter, black carbons, carbon monoxide, nitrous oxide, and many others. I'll show you a few maps from looking at methane across Boston. And so the areas that are blue underneath this, which is pretty much the entire area that's covered, those yellow dots show how much methane was picked up. And when we compare Boston, which is a much older city, to Indianapolis, we see that newer cities have much fewer leaks. And now we'll compare that to Chicago. And you can see pretty much any of the green area or the blue areas underneath, we're seeing substantial leaks in that area. So again, think about if you're a mother and you want to see relative to where your children are commuting, where schools are placed. This is information that has never been public before, and we're trying to do whatever we can to get it out there. One other example, if anyone's interested in fisheries, and I won't spend too much time on this because of our limit, but this is often the state of modern fishing. So there's a 3-month moratorium where there's no fishing in the South China Sea. At the end of the 3 months, this is what's coming for you. So it's a scary day to be a fish out there. And if you were to count all these ships, the next step would be to zoom out one level, and then you get a sense of how many fish, commercial, industrial fishers, are coming for you. And we can zoom out one more time, and you really get a sense of it. And so our view is we have these photos because there's a data journalist that's there and it knows this is happening and is taking them. But how do you visualize this at a global level? How do you take billions and billions of data points from ship traffic and convert that into a dynamic view of where fishing's happening? And so we've built behavioral algorithms that look at how ships move to determine whether or not they're fishing. And our plan is to make all this completely public. And we think that will do a lot for transparency. We think there's lots of applications around enforcement. We think there's lots that can be done around ecology. And the slides come. And the same way we can have a macro view of that, we can actually dive down. Come on. All right, well, that didn't play, but you can click on an individual vessel anywhere in that heat map, and you will see, in this case, this is the Valmetal, which is a Portuguese longliner. And you'll go in and you'll see where they're transiting, which are these straight lines, and where they're actually fishing. So it's another view of very large data sets that we're excited to be able to make for the public. Thank you.
Great, thanks. And our final presentation, Stefano?
Yeah, thank you. Thank you very much, Mr. Chairman. I'm Stefano Attivi, Italian National Research Council, and I'm going to talk about GEOS. This morning during the plenary, Christopher told us about GEO and GEOS, and GEOS stands for Global Earth Observation System of Systems. So I will, as soon as I have my presentation displayed, I will tell you more which are the challenges and what we have done in order to face these challenges, in particular big data, challenges. Since GEOS, as I said, is global, so we had to face, how to interconnect many systems belonging to the 5 continents. Shall I push something or? Yeah, maybe not. Okay. And maybe one more. No? Okay. Okay, so as I said, it's global. So we are really trying to connect systems coming from the 5 different continents is a system of systems. So basically it means that we have no choice. We must build on existing systems. So we don't want to, download all the data produced into one common, tank, but we have to interconnect and build on existing systems. So we mainly, need to, harvest at the metadata level, but not at the data level. So as I will try to explain to you, we have, great, thank you. So, okay, you have seen these slides because Christopher, showed, so this is the GEO, the GEO goal here, and GEO as 99 governmental members, Let me, spend few words about this. As you have, told, GEOS is dealing with at least 9 main areas, domains, that are called in GEOS societal benefit areas, but actually there are also the cross, the intersection, which are called community of practices, and now I think there are more than 10, So we have to deal with all different, domains. We have also seen this picture. It is how we conceive GEOS. So starting from the bottom, collecting, and interconnecting systems. So basically there are many different systems, existing and also coming in the next future, and they belong to different areas. Let's call them, societal benefit areas in order to stay with the GEOS jargon. So they belong to different areas, and we have to build on these systems. So what we have done in the past 10 years was to work jointly in order to develop a common governance. That means, an entire process. So not only IT, not only technology, software, but also the process. So the people, the good practices, etc. And in particular, we have worked on this time let's call cyber infrastructure, which is called the Geos common infrastructure. So this time is software IT stuff, and this was developed in order to interconnect as much as possible, of course, the existing system, providing data to the geos. And that's, that's the real asset, you know. We are building on something that is there and hopefully will stay there. And a new other system, of course, is coming every day in order to contribute to this effort. But then, this is the real system of systems. But on the top of this, clearly, we also, must reach out to other stakeholders, such as, developers, private sector, NGOs, public agency, which want to develop specific products, tools, added value products, and serve the final users. So these are the three main, stakeholders here. And of course, the process is not just a top-down or bottom-up process, but there are also feedbacks, and all the different, stakeholders can influence the process itself. In particular, I will cover today how we have developed a unique and hopefully flexible common interface in order to access the system of systems through, of course, the Geos common infrastructure. And these are the main, the main developers of the main agencies involved so far in the Geos common infrastructure. And in keeping with the, with this process, we have reached out to more than 100 existing systems. Actually, now there are 134. And these are, some of those systems, they are public. I will cover later also a private area. And so we are building on these systems by applying what Christopher called a brokerage approach. And so we developed this brokering framework, which is also, relying on other software components and services, such as the component service registry. So of course we have a pretty good, registry service where all those systems are registered, and we have a pool of semantic assets where we go in order to learn more about some, concepts, elements that are not so semantically speaking clear, because we are working with 9 different societal benefit areas, domains, basically, scientific domains. Then we develop a Geos web portal, so you can go to the Geos web portal, submit your query, request, mainly discoverability and potentially accessibility. So these are the main functions, and through this brokerage framework, you are, connected to these 130 different systems. And now we have been also involved in introducing what are called community portals. So it is possible also to develop, as I explained, specific portals, tools, applications for specific needs. And recently we also developed together with the private sector. So we developed some test experiments in order to add not just public systems, but also private capabilities to the GCI. So this is actually where we publish. It's a public web page, so you can go there and you see, how many systems are now contributing to Geos, and these are the numbers, data set numbers. In particular, the blue ones are completely open and free. Geos really advocate open and free data sharing. As you can see, almost 70% are not completely open and free. That doesn't mean that they are not open. I guess that 90% are open, but when we talk about free, And then, we had to, distinguish about different cases. Maybe you can use it, but you can, redistribute, etc. So this is why we have so, a few blue ones. But we are, of course, improving, and we advocate, the open and free data sharing. The total numbers are 1.3 millions of data sets for something like 200 millions of single elements. So, I mean, you can potentially download 200 millions of single elements or data file. Okay, and what is interesting is that this is a very flexible and open system framework, so more are coming and will come in the next future. So these are our process, these are our numbers. As you can see, I mean, we started with few data systems when we basically decided to embrace this brokerage approach, something like 15, but suddenly, I mean, we added more and more because we are trying to facilitate their engagement, and now we have 130 actually of these systems. In terms of numbers, similar situation. We started with few 100,000, and now we have, as I said, almost 200 millions of discoverable and potentially downloadable elements. And so, I mean, clearly we had to face big data. All the, the challenges, in particular volume and heterogeneity, but also quality, of course. And we moved recently in the cloud, so all the components now are running in a cloud, a public cloud, so that's, a logical schema. Here we have many different supply systems. They are interconnected through this GCI, which is running in the cloud, so leveraging the infrastructure and platform as a service. And what we develop is a software as a service, mainly for mediating, for producing what is needed in order to expose a common view of all these different metadata. And we also develop a set of APIs, so you can use these in order to interface to the GCI and discover and access Geos data. And several clients actually, and portals and tools have done these. So I just mentioned some of them. We have clients from WMO, we have clients from, for example, ARC, GIS, we have CEOs in particular for water domain. We have a Chinese Geos portal, and we have a couple of programs specifically launched in order to develop apps, one by Geo and the other by the European Commission. And what is interesting once more is that this is a flexible, extensible framework. So we support international standards and community standards, of course, OGC, ISO, W3C, and we do that for both the user side and the data provider sides. For instance, this is this brokering framework cloud configuration, and what is, of course, is that we are leveraging these cloud capabilities in order to implement load balancing, auto-scaling. These are the numbers of how it is running today, but the main message is here is that, I mean, the GCI is scalable, due to these, cloud capabilities. And in terms of statistics, this is public as well. We collect and publish usage statistics in terms of all-time, yearly, monthly, and daily statistics for the number of discovered, finalized discovery queries, as far as the most searched keywords, the most searched data source, and the most used query approach constraints, either simple or complex. And these are the numbers for the last year. We have something like more than 400 finalized discovery queries, and for this year we will break 500,000. And the temperature definitely is the most searched keyword, then river discharge. And as far as sources, Pangaea, one of ICSO digital library, was the most searched last year, and the Global River Discharge Center was the second one. And most of our users just use keywords. And the other interesting point is that after keywords, they want to access open and free data. So once more, I mean, we have to push forward this concept, share and share. What about the next future? I mean, this is my personal position, so this is not Geo's position or the GCI position. I mean, what we have seen, we started, I mean, we mean Geos, started developing this GCI in 2005, and we moved in 10 years from a catalog of catalogs to something that was a bit more, flexible, such as a brokering framework. Then we, in order to face big data, move all the system into the cloud. So what next? I mean, definitely next, it is that we have to move on and to, address some of the challenges that were mentioned today in the plenary. So data, doesn't mean, knowledge. And what we need is, effective or compelling, data. So we need to move on and involve more and more experts, people. And as we move from discoverability to accessibility, we have also to now embrace, reusability. So that's my last slide. Actually, now we have a lot of observation in Geos. I'm talking, we are able to, at least provide discoverability and the potential accessibility to many data. What we are now, discussing is how to introduce new concepts, not just observations, data, but also new concepts such as essential variables, indicators. This was also covered yesterday. This is what we need in order to fill this gap towards the, strategic goals by Geos or by, UNEP or others. So these concepts mainly means that we had to collect not just data and services, but more, what is called knowledge or a lot of knowledge bodies. We started, of course, Geos is not just data. We also, collect tools, web pages, documents, but we have to do it more and more, and more effectively. And this is what I call, to move from a data or information system to what is a what-if-based system. So not just to discover, products, but to answer questions, so that the Geos users will be able to access Geos through the GCI and, of course, discover observations, but also submit important and complex, queries, and also to understand how far we are from our strategic goals. And this is what I call to move from a software ecosystem to a social ecosystem. And I've finished. Thank you.
Thank you, Stefano. So we still have a few minutes for questions and comments from the floor. I think we've gotten a good sampling of some of the ways in which people are trying to bring big data out and make it available. Everything from the country level, a single company, a whole discipline, and of course networks and efforts to promote interoperability. So obviously there's a lot more out there, but this is kind of a good sample. So I see a hand over there and one in the back. So
yeah, thanks. Yeah, Ed Parsons here from Google. I think there was a common element across all of the talks, which looked at one of the major V's of big data, which was the volume, and I think everyone kind of dealt with that issue. I saw less focus on some of the other V's, particularly velocity and veracity, much more unstructured data, and the potential of crowdsourced and IoT content that is perhaps less structured than the Earth observation data that we all spoke about. Where do you see the technology changing to take into account those other elements of big data?
So why don't we take the second question and then we'll come back to the panel.
Hi, thank you. That was really interesting. I have, sorry, and I'm Claire from IUCN. I have a specific question for Brian. I thought it was really interesting, the time lapses and the visual representations. And I'm interested in the question on whether you actually collect data on the impact of these data. So basically, if you kind of like look at who's using it and what effect does it have, I think I would find that really interesting to see if that's even possible, and if it is, how to find it.
Okay, Brian, since you had a question directed at you, why don't you go first?
Sure. So I guess your question was, what are the impacts of something like time-lapse? Is that correct? So our view was we'd like to make it public to the entire world. And we didn't really know how it was going to be used. We thought the more we put it out there, the more people come back and tell us stories about how it ended up being used. And that was the advantage of doing it for the entire world. So I can give you a few examples. So from the scientific perspective, we had a lot of people with background in hydrostatics and looking at rivers. And when they watched some of those examples, not particularly the one I showed you, but other ones on how the Nile had been changing, the entire textbooks are being rewritten on that because they thought it was physically impossible, and now they've been able to see that firsthand. From a political perspective, I think some of the examples that we've seen around Vegas, some of the examples we can see when we go to watch the Aral Sea dry up. We met with delegates of the Kazakhstan's government recently, and they're actually doing work to build that part of the Aral Sea back in. And you can see those positive changes as well, and that's really strong. I've had lots and lots of small nonprofits come to me and talk about examples of looking at coastal erosion and using that in local board meetings and things like that to bring pressing issues forward. And with the tool, you have a very straightforward way of copying a URL and sending that to anyone in the world. And there's collections of these online that we just keep seeing and seeing. So while Google doesn't officially track the impact of this, the idea is that it's out there for anyone else to use.
Okay, and then Ed's question about velocity and veracity. Stuart?
Thanks, Ed. I guess I'd make the point that while we're starting with structured big data, the data structure itself is not dependent on that. So in the stuff that I showed you on the data cube, we're effectively translating those measurements from satellite into spectral reflectance measurements at a point in space and time, and they can come from a satellite, they can come from an aerial drone, they can come from, I've got an app here that is used to calibrate watercolour information, so they can be crowdsourced by people out diving. The data structure itself is agnostic to that. It's just that we're working on the biggest data sets to start with. But absolutely, it will be important that our big data structures are able to integrate that community collected data in the same way. What I would say is that the data cube, I mentioned that provenance is a key issue. We track the provenance of every single measurement, and that then allows you to incorporate measurements that may be, to some people, seen as less reliable, because you can then just exclude them from your analysis if that's your want, or if you're willing to take those measurements into your analysis, then you include them. It's just a flag on the data itself. It's not actually saying that the data is bad or good. It's just being collected using one particular technology versus another.
Mark, you also had a comment?
Yeah, so not an expert in this area, but in OGC we take problems like Ed expressed, veracity and velocity. Those are, for some, they're age-old problems, and for others, they're relatively new. And what we try to do is bring a domain of interest in and actually bring industry and users together to determine what architectural approach makes sense to deal with that kind of a problem. So it could be moving the processing closer to the collector or on the collector so that you're only getting data that qualifies as something that needs to be addressed. But that's the whole idea. I think the idea is to bring together the communities with a problem set that's well defined, and then have industry work at it to iterate solutions that will optimize the answer both in technologies and standards. In the last test bed we did, which was focused on a future, if any of you are from San Francisco, I apologize, it was a future climate-induced storm in San Francisco. We actually had in the test bed industry players actually integrated crowdsourcing on the fly to integrate the ground observations with the data they were actually analyzing and projecting to see whether or not there was a correlation. So those types of things I think are useful to look at how the command and control loop works, how the data feeds work, and then where the processing needs to happen.
Stefano, yeah, quickly, I'd like to get one or two more questions off the floor. So,
yeah. Shall I push? Okay, no, it's okay. Well, I mean, my point is that we haven't, developed in Geos, as I told, any of these very fast processing, schemes, and I guess that we are not doing, what you have seen by, Stuart and Brian, but hopefully we will leverage, their work. So, but as far as our experience is concerned about quality and also, about, let's say, velocity in the sense how much data shall we, exchange, so how quick, we must be. Well, our, experience is that we have to understand first very clearly what is the fit for purpose. So, and sometimes this is not so simple because we try to think of a quality level which is absolute. Well, in these 10 years, we have learned that there are different good quality levels. Depends on your purpose. So that's, I guess, what we had to discuss with our community experts and then maybe come up with different targets here. So this is at least what we have discussed so far.
okay, there was a question. Did you still have one up front here? And, okay, and then afterwards.
Thank you for the presentation. Stuart from T-Systems in Germany. And in sense of propagating best practices, it would be very interesting maybe if we could learn what database technology and query standards or languages are being used in those examples that were mentioned, the Data Cube or Google, and if there's any, say, standard on the horizon to simplify say the multi-domain that was also addressed in the talks, or the cross-domain aspects between those data sets.
Hi, I'm Jeremy Tandy from the UK Met Office. So great presentations all. On a number of occasions, you mentioned keep the data where it is, send the query to the data, totally get that. But then eventually you have to get some useful stuff from the data center to the user agent, to whatever it is. So Stuart, you had the example of being able to drill in to the data to get those time series out. And then that provides some really compelling information that you can work with locally. That's an example of one type of API that you might have onto the data. Are there any thoughts about how to, once you've drilled in, you've got that useful piece of information, how to expose those kind of functions as APIs for end users?
So, yeah. Stuart?
Yeah, thanks for those questions. Absolutely, there are emerging standards. We're using, as Mark mentioned, a number of the OGC standards as structural kind of components of the data cube. We use web coverage service, web mapping service. We use NetCDF as the encapsulator of the data at the data chunk level. The code about how we actually tie those chunks together and enable the functionality is all open sourced on GitHub because we're trying to develop this in collaboration with a range of other parties. And coming to the API question, absolutely, the focus for us has been, and I think Google Earth Engine has done this brilliantly, effectively. They've created a platform with an API that allows people to come and play, and in fact they're reliant on people coming and playing to generate products, because it's the community that's generating those products that you saw from Google. We're trying to achieve the same thing. So we've got an exposed API that has defined ways of asking the questions that I showed you, and people from the research community are coming on board to actually run their own code and their own algorithms over our core data cube, if you like. And I see the combination of Google's approach and government-based data cubes having to coexist for a few years. They may eventually all come together in some sense down the track when governments are a bit more comfortable about having mapping in the control of non-government hands in that sense. But I think that those are emerging standards, and the more we can share what we're doing, so if we can learn from what Google's doing, Google can learn from what we're doing, and we share those kind of steps forward, then there'll be emerging standards continue to develop worldwide around this.
Okay, yeah, quick.
Yeah, just a quick comment that maybe also referring to the two previous questions. There are lots of course, emerging standards in this domain, and I would say that it depends less on the type of query language that you use than on the quality of metadata and data that you are trying to retrieve. And there are lots of data available, but typically descriptions are poorly structured and incomplete, and that's where one of the main problems is. So if, in our case, we use a lot of domain ontologies to improve the content of metadata so that to make this data available through queries of different types. Another part of it, that everything that we do with metadata or data is recorded in a provenance track, and there are standards for retrieving that type of information. And certainly if this information becomes available, that contributes to the level of trust that you can have in the data, and addressing one of the big V's of big data.
Okay, well, we are actually out of time, and I don't want to cut into the coffee break too much, but this was a panel that did throw at a high volume, at high velocity, and I hope with a lot of veracity. So let's please thank the panelists for their presentations and the discussion. And I'm sure you can catch up with them during the break and afterwards. Thanks a lot.